Dzień dobry, Szanowni Państwo. Witam wszystkich na trzeciej edycji webinaru Wiedza ma warstwy, webinaru o nowych technologiach, podczas której spotykamy się z liderami na rynku nowych technologii z różnych branż, dlatego zachęcam też do obserwowania naszej strony sygnis.pl/warstwy, gdzie Państwo znajdą wszystkie pozostałe tematy jeszcze w tym tygodniu. Tylko proszę pamiętać, na każdy webinar obowiązują zapisy. Dzisiejsze spotkanie będzie prowadzone w języku angielskim. Po prezentacji zrobimy sesję Q&A, także zachęcam zadawać pytania na czacie, aczkolwiek gdyby Państwo chcieli zadawać jakieś pytanie bardziej specyficzne, można też zgłosić na czacie chęć zabrania głosu i dopuszczę wtedy Państwa do mikrofonu. Okay, now we'll continue in English. Welcome everyone once again in our webinar series Knowledge Has Layers. As I mentioned in Polish, feel free to write your questions in the chat, or if you want to ask question out loud, please write that you want to do it in the chat, and I'll give you the mic then. And during the presentation, please mute your microphones. And now we will go to the most important part. It's a pleasure to introduce our guest, Chief Scientific Officer in Femtika, Dr. Linas. And Linas, the floor is yours.
So, thank you very much for a very kind introduction. It's actually a pleasure and honor to be presenting here. And I will present what we are doing in Femtika, namely our laser nanofactory system and everything which is related to it. So, let's get going. So, what is Femtika? Maybe this is the first question that we should answer. Femtika is a spin-off from Vilnius University Laser Research Center, which specializes in laser micro nano fabrication. We were founded in 2013 when a bunch of us realized that we have know-how, equipment, and the ambition to pursue our goal of actually making this technology widespread and actually making impact worldwide. At the moment, we're based in Lithuania, Vilnius, a place called Sunrise Valley. We actually have around 40 employees, out of which are several PhDs and several PhD students. And this basically paints a pretty good picture about the fact that we are a managed research organization. So basically, we do a lot of in-house research, development, and similar sort of activities. And unsurprisingly, a lot of those are financed by various European R&D projects and national R&D projects. We have several Horizon, Eurostars, Eureka projects, to name a few. And we're also very active in the general scene of photonics and lasers, with being members of various associations and organizations. And we're very glad that we have opportunity working with Sygnis, who are our partners in Poland. We had numerous very insightful discussions throughout the years in relation to the technical part of the fields, because we have some pretty major overlaps, including bioprinting and 3D printing in general. And we're very glad and honored for possibility to work together with them. So this is very short about the company itself, but what actually we are offering. And our primary offer and value proposition lies in combination of additive and subtractive femtosecond manufacturing. Now, all nice big words, what does exactly mean? Well, laser is quite a versatile tool in material processing, and this is especially true for femtosecond lasers, because femtosecond lasers can allow inducing a lot of different light matter interaction regimes that could be used for both additive and subtractive manufacturing. However, throughout the years, it was basically established in the field that if you want to do one of these specific operations, you need a specific setup for that. Well, we looked to it from more fundamental standpoint, and looking very fundamentally, the only primary difference, of course in simplified terms, but it still applies, is the fact that each of these regimes require different light intensities and just different working regimes. But interestingly, because the laser engineering and laser industry is advanced quite far, these days we can actually induce all of these relevant processing regimes with just one single laser, which means that we can actually have a workstation that simultaneously can support different processing regimes, and hence this is why we're offering additive subtractive manufacturing, meaning that all of this can be induced in just one workstation. Namely, we have several technologies at our disposal. I will mention the primary ones. So the primary, first of the primary ones, and actually, of course, the most simple, is just ablation or drilling, also sometimes called cold ablation, cold processing, actually. And the idea here is that because we have very short laser pulses, the interaction time between light and the lattice of the material is actually shorter than the heat dissipation from the affected region. So this is why the laser in this regard acts less as a so to say, a heat source like most of the other laser systems, but more of a cold tool that basically allows to ablate it. And because of that low thermal effect, we have very high cut quality. We have also very simple process at our hands, and basically we can cut fast in basically any material imaginable. Also, if we tune parameters just right, instead of outright removing material, we can actually just modify its surface or partially remove it and partially modify it. And this is what is called femtosecond laser surface structuring. And the idea here is that if we apply it, we can on demand have either hydrophobic or hydrophilic surfaces, which are achieved due to controlled changes in the surface patterns, which can be hierarchical, meaning that they can go from sub-diffraction limited nanometric to basically hundreds of micrometers in overall size. And we can also play a bit with surface chemistry, because if we introduce a special atmosphere during the processing, it basically results in different surface chemistry, which in turn also signifies some of these interactions that we want after the processing. And this can have multiple different applications, including heavy industry for friction reduction or better adhesion, or otherwise in maritime and in aviation industries for anti-icing or anti-fouling, and etc. So this is one of the areas we're working on quite actively as well. Now, these two technologies that I just presented are still more related to 2.5D fabrication, because you still have some limitations due to how you focus your laser light. If we want to go to true 3D, we have to have different processes, and selective glass etching is one of them. And this is a still subtractive process, but the idea is that instead of removing material during the processing, we're actually modifying it in a very specific manner. And what it does, it basically makes it to etch a lot faster when we put it into etching solution, namely HF or KOH. And in this way, we can basically have almost an inverted 3D printing, which means that we etch out basically what was exposed with the laser. And in comparison to, let's say, ablation, we can actually have true 3D shapes, including movable structures like this ball joint chain that we have on the right. And the idea here is that we have an outer layer and inner ball, and basically they are intertwined. And what is important is that it is assembly-free structure, meaning that it was not printed, but fabricated out of a single piece of glass. Also, this allows us to have relatively high surface quality, and it's also a relatively fast fabrication process, allowing to achieve even centimeter-sized structures in reasonable amounts of time. And of course, if we want a true additive manufacturing, we can definitely have it in the form of femtosecond 3D laser lithography, also sometimes known as shoe photon polymerization. And the important part here is that because it's an additive process, which is induced by focusing a femtosecond laser light into photoactive gel or resin, And basically what happens at the focal point is that due to sufficient intensity, a irreversible chemical reactions take place and material basically hardens. While where intensity is not sufficient, basically the rest of the laser path, besides the focal point, the material is not affected. Then we put it into organic solvents, something like acetone or some alcohol. We develop what was not affected by the laser, and we have a 3D structure. And due to this writing process, we can actually have a limited 3D architectures, which are not bound to layer by layer fabrication. Also, the spatial resolution can go to very small dimensions, something like 100 nanometers or less, if it is very desired. Of course, a normal operation, something like 200 or 300 nanometers, is easier to achieve and simpler. And what is most important is that this goes basically head to head with the current polymer chemistry advances. And polymer chemistry is an extremely vast field. Layers were printed with materials out of materials such as proteins, hydrogels, acrylates, elastomers. Requirements is that it should be transparent to the wavelengths we are using, and that it should have sufficient 2-photon absorption per section. And due to this reason, it's very flexible depending on the application. It's easy to use, and we also can integrate structures upon structures, which is very well demonstrated by bottom central and bottom right structures, which are actually, again, intertwined and free movable, one of them being a chainmail-like structure. I will talk about it a bit later, and also a mikrofluidic valve, a ball valve, which acts as a kind of like a fluidic diode operating, allowing liquid to go only to one direction. And all of this is printed in one go, assembly free. And as you see from the butterfly, these structures can also be pretty big, basically going to millimeters or even up to 1 centimeter in overall size. And throughout several recent years, we were working quite hard from bringing this technology from laboratory level use to making it basically a widespread and applicable tool. And these are just few examples of structures that we made over the years. And these can be micromechanical structures such as polymeric micro robots, which is this little squid, which moves when the researcher moves the liquid around, or the Geneva mechanism that is freely turning in the magnetic field, or these structured surfaces that allowed in this case, and maybe I will launch it once again. In this case, it basically allows extreme hydrophilic behavior. Basically, the liquid very easily goes up. And all of this is realized with our system, basically the reason why I'm here, the Laser Nanofactory. And I could actually talk quite long about it and its features, but primary keywords here is modularity and flexibility. And the thing is that this system is, in a lot of cases, when we sell it, tuned towards the needs of a customer. At the same time, because of its modularity, it's also future-proof. Because if one day we will create new technologies or new ways to process materials, we can backwards fit older systems as the modules, allowing newer processing regimes, and some of our customers already doing that. And basically everything I will show you from this moment on, and basically everything I showed so far, will be done with the system unless otherwise specified. And of course, when we talk about the system and then this field in general, of course, we want to go from these just simple toy demonstrations like squid or Geneva mechanism and whatnot to actual functional devices. And for that, we need a field to target. And the field that we're targeting now quite actively is medicine, because a lot of needs of the medical field coincide very well with what we can actually do. Because primary challenges nowadays is that we need medicine to be individualized, basically making sure that each patient is getting treatment or procedures specially tailored towards him. At the same time, we want this to be delivered at point of care. So basically, we want to fabricate whatever is needed as fast as possible wherever the procedure will be carried out. At the same time, it has to be effective. We cannot compromise at this at all, because the medical field requires very high effectiveness. And even nowadays, when we saw how much modern world is dependent on effective medical care, this is signified quite a lot. At the same time, it has to be flexible, so it ties in with individualized aspect of this all. And most importantly, it has to be affordable. Because when you think about it, throughout the years, a lot of scientists and engineers proposed a lot of different device and treatment concepts, but a lot of them fell short just because they were extremely expensive and effectiveness and affordability ratio was just not sufficient. And to tackle all of these challenges that in some ways can actually be counterintuitive to each other, let's say like effectiveness and being affordable, a multidisciplinary approach is needed, and basically only then we can tackle these challenges. And this is where we come in, because with our system, due to hybrid fabrication nature, and because, so for some reason moved by itself, because of the hybrid manufacturing nature, and because we can actually make all of these different devices, this can be actually individualized and flexible. And at the same time, because we can achieve quite huge fabrication throughputs, this can also be potentially quite affordable in the long run. So I will talk about several concepts that we've done over past few years to basically show what the system is capable of. And the first concept that I would like to talk about is macromolecule separator. It's a two-stage device based on a microfluidic chip made out of glass with integrated nanofilters. And because of technology, namely 3D laser lithography, allows to have very fine features down to hundreds of nanometers, we can actually make filters that are good enough to actually filter oligomers or other macromolecules. And if we put several of these filters in one such microfluidic chip, we can actually achieve even several stage separation. And what is most important, this chip is completely passive. In other words, you can basically initiate its effect by plugging a simple syringe in the inlet with the liquid in which you want to separate these macromolecules, and that's it. And because the channels are cut with the laser, and because the integrated structures are very small, it can actually be quite cheap and effective. And I don't know why my slides are acting up today. Otherwise, the target application, our target applications are drug development and drug production. And these days, this is quite an important challenge. Now, for this, we use the same nanofactory setup, and I just wanted to show the insides of it. And the primary idea here is that we have a very flexible laser, a lithium carbide laser, which supports 2 wavelengths. We have an appropriate optical chain to control it. And what else I can actually basically stress is that we also have built-in imaging system, which allows us to track fabrication in situ in real time. And also the linear stages and scanners are synchronized, which allow us to achieve this mentioned high speed of fabrication as well as very high precision. And this is our standard system, and I will show some different variations throughout this presentation, and you will understand why modularity is so important. Now, for this particular challenge, we need 2 different structures that will need to be merged together. So first, we need filters. And basically, we did very simple experiment when we fabricated different pore sizes by changing the translation distances between lines. And basically, we saw that relation is near linear and actually very controllable and quite well repeatable. And pore sizes that we managed to achieve were from around 250 nanometers to 1.5 micrometers. Of course, at very small pore sizes, this start to break due to capillary forces and other effects. So Maybe some more advanced processing would be needed in future, but so far we went for experimental structures with 500 nanometer pores. And at the same time, if you notice, we also made a strong support frame. And the idea here is that due to strong support, the whole structure has a rigidity, but at the same time, we perform what is called dynamic slicing and hatching, and surface of it is not really nice, but it's strong enough. And at the same time, we need channels. And for channels, we use just simple cheap soda lime glass. And basically, it was cut with same laser nanofactory setup. We just replaced standard lens with a spherical lens. And again, because we were aiming at fast fabrication, we noticed that our theoretical profile differs from practical in around 5% margin, but we consider that is good enough. So we have these two different components. Let's merge them together. And we did that, and we integrated filters into channels. We saw good adhesion and good mechanical stability. Our initial channels had quite rough walls, and we wanted to potentially improve it by performing HF etching before filter integration. It helped partially, but otherwise we consider that it's not worth the hassle in dealing with dangerous chemical. But otherwise, in principle, this worked pretty well. And although it doesn't really look that nice in SEM images, otherwise it works just fine, and the structure is quite mechanically robust. So we have a channel system, we have an integrated structure. So the question now is how we seal it. So normally we could use a lot of different techniques such as welding or selective polymerization, but the problem is that we need to have very good alignment, and we also need to have very good optical surface contact. And this complicates the process, and it makes it less repeatable. So our researchers proposed a different idea of using a thermal bonding. And the idea here is that we start with clear polymeric slip, and basically we put it on our glass system, with glass microfluidical system with integrated filters, and we heat it up to 190 degrees Celsius. And what happens is that this clear thermal plastic starts to partially melt and basically bonds to the glass channel system without any additional operations. And this is why I mentioned the advances of polymer chemistry, because for filters, we're actually using quite resilient hybrid organic and organic photopolymer that is not affected by this thermal process at all. So it means that because we can use different polymers, we can actually achieve favorable overall outcome. And because process is actually controllable, it doesn't clog the channels, which is proved by this image where we actually use just simple water with food dye, and we saw no leaks or other defects. However, let's very briefly return to the channel quality. It is good enough, but we want to make it better. So we proposed using of what is called burst mode fabrication, and this is where modularity comes into play. Because instead of standard carbide laser and sharply focusing optics, we actually used a nanofactory variant where we actually have more advanced Coras laser with burst mode capability. And also we replaced simple focusing lens with f-beta lens, which means that we have substantially higher processing throughput. And basically, without going into too much detail, because this is still a far front of photonic science, and this is why, as I said, we do a lot of in-house fundamental research. Basically, burst mode fabrication allows us to control thermal effects even better than, let's say, just simple femtoseconds. So basically, we have femtoseconds and burst mode fabrication. So this allows us to have both meter per second level fabrication speed and substantially better channel walls. And this also results in very good filter adhesion. This can also be sealed with technology I presented before. And this signifies why having modularity in the system is such a powerful advantage. And overall, these channel systems are now provided to our biochemist colleagues, and they are now doing filtration experiments, hopefully as we speak. So this is the first concept. The other concept is mechanically flexible scaffolds for cell growth. So scaffolds are quite a vast field these days, and the idea is that we make a structure which allows us to either perform research on cells, or potentially allows us to cultivate cells for different uses, or basically allows us to grow cells for implantation in a living body. And these are very promising prospects in biological sciences. The problem is that most of the normal materials that are used in this technology are rigid in mechanical sense. And of course, body is moving constantly. So putting something rigid into a moving body might not be a best idea ever. So basically, there are two choices. One choice is potentially to have a flexible polymer, and albeit these are coming along when we're experimenting with them as well, there's still a long way to go before we can proceed from proof of concept level fabrication to highly efficient fabrication. So another way is to actually tap into potential of having a geometry of a structure which is shape-shifting in some way. And this can be either a very small balls that can actually shape-shift into a wound or a disease-stricken place, and basically have an adaptive shape like that. And of course, cells are living in these little burr balls. Or alternatively, we can actually look back to the Middle Ages and just fabricate something like a chainmail. And for that, we also use a different nanofactory version. This one is actually using a lot simpler, a lot cheaper fiber laser. And this allows us to have just polymerization, but at a lot higher speed, because when we have oscillator, we have high repetition rate. And this is good in terms of the fact that pulse overlap is higher, and we can actually potentially have bigger fabrication speeds. So this is the reason to use different laser sources, and this is the consulting that we provide when we understand what our customer needs. Now, to fabricate these structures, and again, to make them affordable, we have to make them fast. So to demonstrate how we can increase fabrication throughput, we actually wanted to do these experiments in different fashions. So one way is to just plainly increase translation velocity. This is the simplest way to do it. But at the same time, there are some fundamental limitations how fast you can go. So what about if we play with the algorithm we use for fabrication? So simplest way, we start with 10 on 10 ring array. We start with the standard fabrication parameters, which is 1 centimeter per second translation velocity for synchronized motion, or actually 10 centimeter per second if we use only Galvo scanners. And we start with just raster scanning of the whole STL model, including all of the gaps. And then fabrication time for just the simple small structure is around half an hour. However, if we do just simple mathematical optimization following the traveling salesman algorithm, we can actually reduce fabrication time by, well, basically the 4-time margin, which means that only the mathematical considerations and mathematical optimization, which is built in our standard software, ring fabrication from each other and fabricate each ring individually. And then, because the scanner working field is big enough to accommodate one ring but not all of the structure, we can fabricate each ring individually, which allows us to use scanners and then motion of the linear stages to go between to go between these rings. And then if we use the higher fabrication speed, we can actually reduce fabrication time even more. And if, of course, we use just simple translation velocity, it's surprisingly even slower by around 1 minute. But otherwise, when we fabricate our structures, we have to take into account both how to optimize it from terms of system capabilities and how to exploit those system capabilities by optimizing more than one order of magnitude. Now, when we fabricated these structures, we saw that they are moving quite nicely. Of course, for medical use, we need a bit bigger structures, basically, again, as I mentioned, in millimeter size. And we're using material which is shown by other groups to be biocompatible. And at the same time, it provides good mechanical rigidity and stability during the development process, as well as during the manipulation needed for biological experiments. And talking about those, when we talk about biological experiments, our partners in Lithuanian Healthcare University actually did some initial biocompatibility testing, and this showed to be quite promising. And as I said, structures survive manipulation just fine, although they need to be pushed to side or positioned appropriately. Cell adhesion to the scaffold is also quite satisfactory, which means that this can actually be used as an implant to, let's say, a moving tissue, or alternatively as a shape-shifting scaffold. And basically, at the moment, we're preparing samples for quantitative cell survivability analysis, as well as movement of chain mail with cells attached to them, because basically no one tried this before. And my slides are trying to jump to the last topic because I see that I'm running out of time, but this will not be that long. And finally, it's additive manufacturing of conductive structures. So in Femtika, we can additively print out of polymers, as mentioned before, actually different kinds of polymers. We also have ceramic fabrication capabilities, which were presented throughout the year, so I didn't include it here because for us it's almost old news. But now we're moving to conductive structure fabrication. And you can do it in two ways. You can do it either as direct fabrication, which is very slow, tedious, require very specific materials, and it requires a lot of development. Or we can actually metal plate pre-existing polymer structures. And the advantage here is that we can actually use basically standard materials, which means that fabrication throughput and achievable geometries are quite good in comparison to these just barely 3D structures presented by other groups. So how does it work in practice? So in practice, there are some chemical steps, and I will not go into too much detail here because this is quite a hardcore science, and I would like to keep it simple. But we start with just simple photopolymerization. An important part here is that we have special groups attached to our standard silver meiotis to these structures, which basically means that we have standard polymer with special additive that then bonds to a metal ions. And then we can actually perform silver ion reduction in a special solvent, which then results in plating of this material. So there's a lot of chemistry, a lot of fancy images, but overall what it means is that we have a way of metal coating polymers, and what is most importantly, this is a selective process. So if we have the special polymer structure, let's say in a glass channel, the glass channel will not be metal coated and polymer will be. Great, so where can we use this? And to use this, we propose electromechanical flow meter concept. And the idea here is that we are basically combining a valve and a spring into one structure. So we have a stationary wall, then we have a moving valve, and because both of them are metal coated, that gap between the valve and the stationary plate basically forms a capacitor. And as it moves due to the flow of the liquid, we can measure the capacitance, and in turn we can determine the flow rate and flow direction, which is very important. And if the flow rate is too great and spring might break, we have a valve that basically shuts it down automatically. So this is quite a neat idea. We actually show that fabrication of such structure is not that difficult, and we can definitely perform it. And one of the most pressing questions that we had was can we have a metal layer that is thick enough to support a current going through it? And what we saw is that even at very thin coatings, let's say 10 or 20 nanometers, we actually have a good enough resistance, low enough resistance, and this means that we can actually use it for this sensor or any other microelectromechanical structure fabrication. So this means that this is quite a huge prospect for real 3D MEMS structures. And what is more importantly is that these structures can be integrated into other structures. And basically we have here this spring structure in a glass channel. And a glass channel was etched, again, owing to the possibility of having this hybrid fabrication capability. And overall, it also means that we can actually have integrated structures within integrated structures that also tap into advances of polymer chemistry, as mentioned before. And this brings me to my conclusions, and they are actually pretty simple, is that direct laser writing is a very powerful tool, and we'll see a lot of possible applications in biomedicine. And this is due to the fact that we can have huge tunability in single feature size, in overall size. We can very freely choose materials, and basically we have very limited limitations in terms of what geometries we can achieve. And what is most importantly, this is available. This is not some technology locked in some university lab and basically working once every full moon for publication. This works repeatedly. This works when it's needed. And basically, it's a commercial state of the art, which is available commercially. So thank you. And actually, I have to apologize. I don't know why my computer star is acting up and doing automatic animations. So otherwise, thank you for your attention and your patience.
Thank you so much. Now is the time for the questions. If you have one, please ask on the chat or write down that you want to ask it out loud. And now I'll read the first question. Could we use this technology to create biocompatible microfluidic systems? And if so, which materials could we use?
So actually, this is a very good question. And actually, my short answer is yes. Now, when we talk about biocompatible, to my understanding, most of the glasses are biocompatible. So basically, here's your answer. You can use it. You can just make simple glass microfluidical structures, and we've done this over the years. If we look more to polymer side, we actually worked and are working with some hydrogels, including GELMA with lab photoinitiation, as well as polyethylene glycol, diacrylate, and related biocompatible photoinitiators or without photoinitiators at all. We're also working with, we also have a supplementary technologies such as soft lithography or nano-imprint lithography, which basically allows us to use laser-made, very precise structure to make microfluidical channels out of PDMS. And this is used in biomicrofluidics quite extensively. And actually, last year, we published an article with our German partners where we actually made some PDMS and SZ-based microfluidic systems for organ-on-chip applications. So short answer is yes, it depends what exactly is needed, but we have quite a lot of freedom in both design and material choice.
Thank you for your answer and for the question. And yeah, please write down your questions, and maybe if someone will have some specific questions, they can write directly to you. So
Yes, Yes, definitely. And if you're interested in these slides, I can send them as well. So just please contact Sygnis, or please you can write directly to us, and we will be happy to provide the slides. And if I understand correctly, this meeting is recorded, so you can definitely look it up afterwards.
That's right. Tomorrow we will make sharing of the recording to the people who were registered to this webinar, so don't worry. Okay, so no questions now. So yeah, please feel free, if you will have some questions later, to write to us, to Sygnis, or to link us directly. And now we will finish slowly. Thank you so much for joining us. Thank you, Linus, for sharing your knowledge with us. And yeah, I want to welcome everyone to the next webinars that will take place at 12 and at 14:00. Feel free also to visit website of Sygnis and Femtika. And thank you so much for participating. That was a pleasure. And have a nice day. See you on the next webinars.
So thank you for having me here. It was a pleasure, and until soon. Goodbye.
Thank you so much. Bye-bye.